Hello. This is Sreenadh. Can you hear us?
Yes, I can hear you.
Hi. You cannot see us.
Yeah, I can't see anyone.
Hello. This is Sreenadh. Can you hear us?
Yeah, they're doing something.
Hello. This is Sreenadh.
Oh, it's gone here.
Hello.
Professor Sreenadh, can you hear us now?
Yes, I can hear you.
Can you try speaking something so that we can check if your audio is clear?
Yeah, I can hear you, but with low voice and some disturbance.
You are muted.
I'm muted? No, I'm not muted.
Just give us a bit of time. We are just fixing the issue.
Sure, sure. Yeah, now I can see the hall.
Chat box, we can ask you to log out and log in.
Now I can see. Now I can see the hall.
To send this slides to the
So, Professor Sreenadh, can you try speaking again a bit?
Yes, I can hear you all. I can see the hall also. Yes.
Now it's fine. Now it's fine.
Now it's fine. Yeah.
So, really sorry for the interruption. We had some problems here. So now I think everything is fixed.
You give me some mic or something like that, or I will talk like this. Yeah. I have to talk to him, or I have to talk to this.
So,
Talk to the camera, please.
just stand here, you can see it.
Okay.
Yeah.
Hi, Sreenadh.
Good morning, sir.
Okay, so let me start introducing my I become to here, Sreenadh. Sreenadh is PhD from right. I don't know which year he is here. And joined by the Delhi, and he is a professor there. And let me read his title. Ali livelihood solo critical exponent problems. Sreenadh,
Yes, sir.
yeah, go on.
Okay. Thanks, Professor Pani. I thank the organizers for inviting me for this invited talk. So I hope you can see the slides that I shared.
Sir, can you make it full screen?
Can you make it full screen?
Just one minute. Maybe I have to stop sharing and then I do.
Go to view and make it full screen.
Sharing part, you have to make it full screen and then share.
Or you can keep this side.
First make
I don't know where to do this full screen.
Sir, you can press Control and L together. It will full screen.
No, that does in my screen, but I can't share. After that, I'm not able to see the Zoom.
Oh, so can you keep this sidebar? Yeah.
Sir, on the sidebar, there is a small arrow. Can you click on that?
and just do control plus.
No, it doesn't work.
Okay.
Yeah, I guess it's fine. We'll go with it.
Yeah, go ahead.
Okay. Okay. So I don't know, something else came. So okay, fine. So this is today I aim to present some recent results of me and my collaborators on the positive solutions of elliptic problems that involve critical terms which are of this type, the I mu star with mod u power p. These are something like a convolution terms that I will explicitly show it a little later. So this where here we consider omega to be a bounded domain and lambda is positive, and this I mu is the race potential. And Fu is a perturbation term which is of the type u power delta, where delta can be a negative exponent. And this is all these works are the joint works with my students, former students, Divya Goyal, Tupina Mukherjee, and my collaborators, Jack Giacomini and Radulescu. Okay, so these are the main papers where the first paper was is on the singular problems, where we studied the problems with singular nonlinearities, and we showed how one obtains the minimal solutions and the mountain pass solutions. And the second paper is on the regularity results for this type of problems, and which includes even the problems with the fractional Laplacian operator. And the third paper is about the high energy solutions, which are basically the Coron type of problems, which the domains which are of in the form of annular type of domains. And the fourth paper is again some critical exponent problems on non-contractible domains, where we showed that there are, in the non-homogeneous case, there are more than 2 positive solutions. We showed up to 4 positive solutions. And the fifth paper is about the critical exponent problem for the fractional Laplacian, and the last one is about the extension of these results to, or the Bridges-Nirenberg type of results to Korn Laplacian on the Heisenberg groups. Okay, so this whole research in this critical exponent problems starts with 2 important inequalities. One is the Sobolev inequality, which needs no introduction here. So you have a type of inequality where there is a sharp constant S, and it is known that this constant S is not achieved in the domains, and it is achieved by only the functions which are of the type U. And You can see here this 2 star is 2n by n minus 2. So what happens in n equals to 2, the critical behavior is explained by the Moser-Schrodinger inequality. Though I will focus mostly on n greater than or equals to 3 kind of problems here. So another inequality is the Hardy-Littlewood-Sobolev inequality. So if I take f in LT and h is an LR, where t and r satisfies the relation that is mentioned here, that is 1 by t plus mu by n plus 1 by r equals to 2, then there exists a short constant c, so that this integral on the left-hand side, which is of convolution type, is well defined. And again, this inequality is achieved by the functions of this type. Functions of the type h. Okay, so if I take this, the function f equals to h, which is equals to mod u power p, where u is in a Sobolev function, h1 function, then this integral, the double integral here, if this is well defined, provided this p lies between these two exponents, where these two exponents, lower one is 2n minus mu by mu, which is called the lower critical exponent, and the 2n minus mu by n minus 2 is called upper critical exponent. So this upper critical exponent is something which plays the role of kind of Sobolev critical exponent 2 star, but here it depends on mu also. Okay, therefore you have like in the Sobolev inequality, we have an inequality like this, and we can define, we have this S, which is the minimum of this norm square, okay, under the constraint that u star equal L2 star norm equals to 1. And similarly, one can define this SH, which is the constant, first constant, which is coming from the Hardy-Littlewood-Sobolev inequality. And then one can show that there is a nice relation between these two. This SH is equals to S upon C n mu power minus 2 by 2 n minus mu, and this is proved by these people, Gao and Yang, in this journal in 2018. Okay, so this all these critical exponent problems basically are based on two important results by Bridges and Nirenberg. And first problem is directly by Bridges and Nirenberg, and second one is motivated by them. The first one is about the critical exponent problem, which we know that if you take, as I mentioned earlier, the Sobolev inequality is not achieved in the bounded domains, and therefore you try to perturb this critical linearity there, and then try to see if there are solutions for this. So that is the first paper of Bridges and Nirenberg, which is also known as the Yamabe problem in the differential geometry. And this problem has been, these results have been extended to several extensions people have done. Some of the important extensions are to the Laplacians and also the 2 dimensions. What happens in case of n equals to 2 by Adimurthy and Yadava and these people, and anisotropic problems, Hardy-Sobolev equations, and so on. In case of the problems, the unit ball, the solutions become radially symmetric, and therefore you have the uniqueness results. And later, another result of Bridges and Nirenberg, which I will tell you later, about the local minimizers. Okay. Based on that, when you take instead of superlinear perturbations, if you take the concave perturbation, then what happens to this the solution profile? Then the solution profile changes. Then there, instead of uniqueness, you get the 2 positive solutions. And again, these results have been extended to the Laplacians and critical dimensions and singular problems and so on. And of course, when you take the problem in the radial, in case of a ball, then you have the exact number of solutions. Okay, so these are the complete kind of directions that one studies in these based on these 2 results. So what is the critical exponent problem? So exactly this problem reads like this. The minus Laplacian of u equals to lambda u plus u power alpha, where alpha lies between 1 and n plus 2 by n minus 2. So the basic idea is to try to study the solutions as critical points of this functional. Okay, so this, once if you have a functional like this, then you can show that it satisfies mountain post geometry around 0. And therefore, main idea here is to study the local placement sequences. That is, you have a placement sequence below the critical level, or which is called the first critical level. That is 1 by n is for n by 2. And these sequences are going to be compact. Okay. And how to one show that below this level there is a placement sequence is using these blob functions or these Tarantine functions, which are actually coming from the minimizers of this inequality. Okay, so this is the basic idea, and one can extend, or you can expect the similar results for when you take the linear perturbation by a superlinear type of perturbation. So the solution profile, the bifurcation diagram here looks like this. That is, in subcritical case, you have the bifurcation actually starts from lambda 1 and goes to some finite norm u. And in the critical case, this bifurcation diagram blows up as lambda goes to 0. So the next one is as I said, the concave and convex combined effects. And so in this case, the Q here is less than 1 and it is positive. So this is the paper I was mentioning about in the Journal of Functional Analysis by Amrasity, Bridges, and Ceramic. So here in this case, what happens is that you have a minimal solution, that is U lambda. And also, once if you have a minimal solution, you try to get another solution, possibly because of the superlinear growth of U power alpha, which may be of Montan Pascal. So that is what the Bridges, another result of Bridges and Nirenberg. It's on sublevel versus local minimums. So basically, you try to use the Hoff-Maxim principle to get the first solution to be a local minimum in the C1 topology of this functional J. So if it is a C1, if it is a local minimum in the C1 topology, then does it become a H1 local minimum? Once if it becomes a H1 local minimum, then one can, or the sublevel local minimum, then you can try to apply the Montan pass around this. So that's the idea. So U lambda actually becomes a local minimum in the H1 topology, and therefore you can expect the second solution to be U lambda plus V. V is some non-trivial function, and therefore then this V satisfies another elliptic equation, which is a translated problem. And therefore this problem can be again studied, and this problem one can show that it satisfies this functional I satisfies the Montan pass level, Montan pass geometry, and we can show that the first critical level still this you can have placement sequences below the critical level, and this below the critical level these sequences are going to be compact in H1. Therefore, we get a second solution. So this is these are the two important results that motivated our research in the last several years. So now we want to see the similar type of results, whether they hold for the critical exponent problems that are motivated from the Hardy-Littlewood sublime inequality. Okay, so in case of the concave convex bifurcation diagram looks like this. That is, you can see that from there is a one capital lambda, where from there are two branches. One branch goes to 0, that is a minimal solution branch, and the other branch goes to infinity in the critical case, and the subcritical case it goes to a finite. Okay, so this came another important problem in this is by Hytho, where he studied the problem for the singular norm, that is U power minus Q, where U is 0 on the boundary. Therefore, this nonlinearity is blowing up on the boundary. Okay, but he took the problem with Q less than 1. And he generalized basically the results of Amrasity, Bridges, and Ceramic. And then another problem naturally the question people will ask the question, what happens for all Q greater than 1? So this Hirano and his collaborators, they showed that these results can be extended to all Q less than all Q. But here the solutions are not always the H10 solutions or the finite energy solutions. They are you can define because it's a Laplacian, you can define the distribution solution, but you can define the solution to be L1 intersection with H1 lobe. And I'll show you this kind of results when we extend this to the Hardy-Littlewood sublime inequalities. But here we assume that U is in H1 lobe, but U minus epsilon plus is going to be in H10 for all epsilon small. In this case, these problems are also generalized to the P. Laplacian case, but largely the P. Laplacian problems are open in the singular problems. So one of the results is Giacomini and his collaborators, they showed that for Q lying between 0 and 1, these results can be extended. And in the radial case, we proved that these results hold. That is, the radial solutions, we have basically the Ambrosity bridges ceramic results hold. The basic difficulty here is that both these papers assume they follow the approach based on the Perron's method, which is not clear how to implement it for the P. Laplacian case. So that's why these problems still remain open in this in case of P. Laplacian. That is a similar nonlinearity case. Okay, so coming to this hard irreducible inequalities. So there could be many papers before this, but where we started seeing these results are from the papers of Morose and Schaffzen. This is published in 2013. So where they studied the ground state solutions and some kind of radially decreasing nature of these solutions, but in the whole space. Okay, and also they showed that if your P is more than the critical exponent, then there is no solution for this problem. So also there was another paper by the same people in the transactions of AMS, where they showed that in place of mod u power P, you can take a general growth function, mod f of u, but in general satisfying something like the general conditions, more general conditions of the very sticky and dense type of conditions. Okay, so what happens in the bounded domains? So in the bounded domains, does one consider the problem of the Bridges-Nuremberg type of problems, and do we have the existence of solutions and non-existence type of things? So it started with 2016 by Prof and Yang. They started working on this problem. So if you see the critical nonlinearity, this is what I was saying, that I alpha star convolution with mod u power 2 star. So here you have mu less than n and 2 star is the critical exponent. So they studied the Bridges-Nuremberg type of non-existence and non-existence results. Also, they studied something like non-homogeneous problems and some type of convex concave combined effects, etc. Okay, so in this case, again, one can show that the first critical level is looks like this. That is 1 n plus 2 minus mu by 4n minus 2 mu into sh or 2n minus mu by x. Okay, so below this level, the placement sequences are going to be compact. And one can obtain the minimizers of this equality in this form, and you can have the placement sequences below this level like this. Okay, so after this, where our first results were started with the regularity results. So the regularity results, that is, you take the same problem, that the Bridges-Nuremberg type of problems, with the conditions on f satisfying the superlinear type of growth, which is like this. That is mod tft less than or equals to constant times mod t power 2n minus mu by n plus mod t power 2n minus mu n minus 2. This is basically the lower and upper critical exponents. And once if you have a problem like this, and if you have weak solutions, all these weak solutions are going to be how regular, that is, they are infinity functions. Once if you have an infinity nature, then you can apply the elliptic regularity to show that they are actually the C2 alpha. Okay, so these results also hold for the fractional Laplacian case. In fact, our paper actually we wrote for the fractional Laplacian, but the results are new for even for s equals to 1. So the fractional Laplacian is defined for s lies between 0 and 1, and the fractional Laplacian is defined as the principal value of the integral of ux minus uy by mod x minus y power n plus 2x. And g is a perturbation term. Sorry, there is a typo here. U is not equals to 0 and omega, u equals to 0 in Rn minus omega. Okay, so the functions, the solutions or weak solutions, finite energy solutions, are defined as the functions u in H10, which satisfy this equation, like the same type of things that you have in the case of critical exponent problem. Okay. And the associated functional looks like the j, which is half of norm u square minus the primitives of these functions. Okay, so what is the main result? The main result is that the perturbation term that we assume is, if it is of the type of mod e power 2 star minus 1, here the 2 star is the critical exponent. And of course, the other term, that is the Hardy fluid subload term, will be there. That is also up to the critical. And if this condition is satisfied, then you have the solutions to be L infinity and intersection with C2 lobe. And of course, they are, since I'm taking the problem in Rn minus omega, for the fraction, it is going to be C2 lobe, otherwise it is going to be C2 alpha in omega. Okay, so I will briefly give the idea of this. The proof of the idea is to first obtain the Bridges-Carto type of non-local version of this Bridges-Carto type of things. That is for the, which is for this type of non-local equations of the convolution type. Once we establish the Bridges-Carto type estimate, then we try to basically increase the integrability of the solution, right, beyond the critical exponent, beyond this 2 star. And that is can be done by some kind of approximations or some kind of truncations of this nonlinearity. So the truncations which are of this type here, that you take eta for large, you take it to be 0, and eventually you are going to take L to be large enough. Okay, so this is all the truncation arguments. We truncate this H and K by Hn and Kn, satisfying that mod Hn will be less than or equal to mod H, and Hn converges to H almost divided. And you have this Bn Vw, which now become bilinear forms, and therefore you have by Lax-Milgram lemma, you can have a unique function Un. And this Un actually converges to U weakly. And you can do now some kind, based on this truncation arguments and some measure theoretic arguments, one can use Hardy electrode subload inequality to show that this convolution term actually going to be L infinity. Once if we have this to be in L infinity, then you have the standard elliptic regularity. You can have this problem to satisfy something like minus plus in U equals to kxu, where k is bounded by c into 1 plus mod e power 2 star minus 1. You can reduce this problem into this, and then one can, once if we have this, then one can use the Moser equation to get the L infinity estimate. Once if you have an infinity estimate on the solution, then you can use the standard elliptic regularity theory to get the C2 regularity. Okay, so an important application of this is to the H1 versus C1 weighted minimizers. So that is, if you, as I mentioned, the Bridges and Lindenberg result, that is, if you have the U to be a local minimum in the C1 topology, whether that is going to be the local minimum in the H1 topology. So that can be proved using these regularity results and uniform estimates that we showed here. And another application is that if you have a subsolution and super solution, and if these are not solutions, then you can actually try to use the Perron's type of arguments to show that there is actually a solution between these sub and super solutions. And so this is another important idea to get the multiplicity of positive solutions. That is the Amorosity Bridges and ceramic type of, that is concave, convex perturbations. Okay, so the other one is the look at the singular problems, whether we can get even in the singular case also, whether we can get the solutions to be the regular solutions. Okay, the H1 solutions to be the regular solutions. You can do that. The simple idea is to look at the purely singular problem, that is minus of plus in U equals to U power minus Q. And this problem is well studied. So this problem, you can show that this is greater than or equals to constant times Phi1. Phi1 is the first eigenfunction, or the positive eigenfunction for the Laplacian. And once if we have this, then you can see that this term, the singular term, that is U power minus Q, can be controlled by something like a linear term on the right side. Okay, look at the last term, that is looks like characteristic function of U less than beta, U by C1 square C2 D square into beta power 1 minus Q. So the singular term is controlled by something like a linear term. And then one can use the similar type of ideas that were there in the previous theorems to show that the solutions are going to be infinity. And once if you have infinity, you can use the electrical clarity to get the smoothness, the C2 regularity. Okay, so the other one is the, as I mentioned, that is, this is up to the, what previous works are up to the Q less than 1. So what happens for Q greater than or equals to 1? So one can try to use the non-smooth calculus. That is what I mentioned, the Hirano and their results. They can be extended again to this type of hard load critical exponent problems. Results, yes?
You have a couple of more minutes.
Okay, I will quickly summarize. So these results can be extended to this type of problems, and these results are also hold for the fractional Laplacian problems. Okay, so I will skip this, most of the things. I will just go to, yeah, so these high energy solutions, one can, as a next step, we study the high energy solutions of the Coron type of results. So here we consider a problem of this type, and where F is a non-homogeneous term, and based on the norm of the non-homogeneous term, then can show that there are multiple solutions. So these are the two papers. We wrote that if you have an annular type of domain, then F is a non-negative, and F is small enough, you have actually up to 4 positive solutions. Okay, so I will skip all these things. It depends on the category theory and use this. So some of these generalizations for these problems are also studied by us. First paper is the Bridges-Nilbrook type of problems for the fractional Laplacian, is studied by Tuhina Mukherjee. And also these problems, as I mentioned, the critical dimensions, that is in case of n equals to 2, the similar results are obtained using the Moser-Schrödinger inequalities. And also these results are generalized to the Cohen-Laplacian on the Heisenberg groups by Divya and myself. These are some of the generalizations we did, and of course there are some more also are there, important generalizations. So what are the, again, some of the open questions here is whether one can study the regularity results in the P-Laplacian case. So in case of this mu, that is the Riesz potential mod x power mu, right, mod x power minus mu. When mu is small, one can use the Moser iteration technique. So this recent paper I saw in the archive. But generally for mu large enough, that is mu up to n, it is not clear how to proceed to show that I mu star mod power q is in L infinity. That is one. And the other one is the P-Laplacian case, the Bridges-Nilbrook type of results. So in this case, whether how to prove these things, because we don't have any idea of the minimizers and the critical embedding and the first critical level, or even the best constants, whether the best constants are achieved, not achieved. These are all completely open questions. And sub-Laplacians on the Carnot type of groups, because we did, when we were doing this results on the Heisenberg sub-Laplacians, we were told by Anusita that she brought to our notice about her paper. So basically the idea here, the problem here is in the Carnot groups, we don't have the minimizers, exact form of the minimizers. So maybe one can use the ideas of these two people. They don't have the exact minimizers, but they have some information about how these minimizers behave at 0 to infinity, and therefore one can try to use that to get some existence results of Bridges and Nilbrook type. So these are some of the things that still open questions, and if anyone interested, you can pursue this. Yeah, thank you very much. Any questions?
Any question? One quick question.
Yes.
What about, say, Neumann boundary conditions or something?
Neumann problems?
Yeah.
Yes, one can try to do that, but we didn't explore. Yeah, you're right. Neumann problems. You mean to say something like double critical exponents, the Neumann boundary
conditions. If you change the boundary conditions, the question is, if you change the boundary conditions, will the analysis go through?
Mostly it should go through. There are some papers which we wrote earlier with some of my PhD students in the P. Laplacian case, but not with Hardy liquid. But one can try to see that. We didn't try that, but one should generally work. But technically, one has to see whether.
And what kind of practical problems this is? You may not, you need not answer it, but just in case you know.
No, I am not aware of. Maybe you can see the papers of Morose and Chopin. They write some applications to some physical problems here.
Thank you.
The lambda I have taken is a fixed one, or is it some parameter?
Lambda is a parameter. Normally, the lambda varies from 0. Always take it to be positive. Yeah.
You didn't put any condition on that, right?
Any condition of?
0 to 1, right?
Lambda is positive. Lambda is greater than 0.
Any positive constant.
Any positive constant, yeah. Any positive parameter, and the solutions existence and non-existence depends on the on parameter lambda, right? So for lambda,
does it affect the
yeah.
The lambda, does the lambda affect the solutions or whatever this?
Right. Right. So
or any size of lambda.
Right. So for small lambda, you have solutions, right? For even the Bridges-Nirenberg type results, you have lambda less than lambda 1, you have solutions. For large lambda, you don't have solutions. The same thing here, Bridges, Ambrosity bridges in ceramic. If you see the bifurcation diagrams I showed, they show that for lambda large, the solution is only trivial.
Solutions trivial.
Trivial, yeah. Yeah, this one. See that for lambda large, there is no solution. No
lambda, so there exists a capital lambda beyond which it is not.
Yeah. So the solutions are going to be trivial solutions. No positive solutions.
Yeah.
Because online people have.
Any question from online people?
Professor Sreenadh,
Yes.
in most of the problems we have taken critical exponent with the standard Laplacian. So are you going to look at the problems with more general differential operator on the left hand side, not just Laplacian?
Yeah. That's right. So not more general means you mean to say the elliptic, general elliptic?
Yeah, generally let's say with varying coefficients and with the jumps in the coefficients of the PD. Linear ones.
Yeah,
but more general.
Should work, right? Yeah, generally it should work because for the Laplacian to whatever you can do from the Laplacian to the second order strongly elliptic equations, it should work.
Yeah.
Okay, so let us thank Sreenadh again.
Yeah, thank you very much. I see the large crowd there, so I really miss visiting Trivandrum. So in the last 2 years, I did not travel anywhere due to the fear of.
It's not come here.
Yeah,
The punishment for you. That is why I got down the things.
Yeah. So I'm sorry for that. I'm not able to. My family.
So there will be tea in front of the seminar. Only 5 minutes free break. Or maybe less than.
Thank you very much. Yeah.
Okay, thanks.